Our speaker for today is Professor Manmohan Kapur. Professor Kapur received his PhD degree in 2003 working under the supervision of Professor Ganesh Pandey at National Chemical Laboratory, Pune. In the same year, he joined the group of Professor Jane Kuncha at the Wayne State University, Detroit, USA as a postdoctoral fellow. In 2004, he was awarded the prestigious Alexander von Humboldt Postdoctoral Research Fellowship for his second postdoctoral stint at the Institute for Organic Chemistry, University of Tübingen, Germany, under the guidance of Professor Martin E. Meyer. Upon his return to India, he joined the industry before moving to the Indian Institute of Science, Education and Research, Bhopal in 2009, where he is presently a professor in the Department of Chemistry. His research interests include the total synthesis of natural products by employing transition metal catalysis as a key step and synthesis of natural products bearing peptide-based backbones, especially certain classes of antimycobacterial agents. He is the recipient of the Bronze Medal of the Chemical Research Society of India and the Serb Star Award, Golden Jubilee Visiting Fellowship of ICT Mumbai. He is also the member of the International Advisory Board of the Asian Journal of Organic Chemistry and an editorial member of Tetrahedron and Tetrahedron Letters. He is also an elected fellow of the National Academy of Sciences, India, Prayagraj. Thank you, Professor Kapur, for joining us. The stage is all yours now.
Is it visible? Everything?
Yes, it is perfect. Please go ahead.
Okay. Thank you so much. Thank you so much, Dr. Jha and Professor Gogoi. And I'd like to thank the ACS for the kind invitation to present some of our work here. And a very good evening to all of you, and a very good morning to all the overseas participants. Today, we are going to talk to you a little about Distal C-H Functionalization using Electrophilic C-H Metallation. Before we go ahead, some of the research themes in our group are essentially proximal CH activation, which forms the major mainstay of our research group. And what I'm going to talk to you today is essentially the distal CH activation. So this is what I'm going to talk to you about today using electrophilic metallation. We also do a little bit of distal CH activation using large cyclophane-like pre-transition states. I'll present a couple of works to you today in that particular regard. And then there is a major research area in our group where we do the remote indirect functionalization using preformed enolates. There we use low-valent transition metal chemistry. And then all of this culminates into natural product synthesis, where we use transition metal chemistry, CC bond formation reactions to make a couple of peptide-based antimycobacterials and macrolactone-based natural products. So moving forward, in the last 3 decades, transition metal catalyzed CH activation and functionalization has become a major research area all over the world. So what exactly is CH activation? CH activation essentially is the conversion or the replacement of a strong CH bond by a weaker C metal bond, where the metal usually and most often is a transition metal. The replacement of this CM bond by an electrophilic functional group leads to the process called as CH functionalization. So essentially, CH activation is a subset of CH functionalization. So why this is so important, and what are the challenges associated with CH functionalization? So generally, the CH bonds are quite unreactive due to a large kinetic barrier for bond cleavage. You can see here the bond dissociation energies are decently high and are one of the highest when it comes to a hydrocarbon. And this stems essentially from the fact that the carbon and hydrogen have essentially very similar electronegativities. Not only that, when you look at a hydrocarbon, CH bonds are quite ubiquitous. Essentially, they are found in similar chemical environment, and you have more CH bonds than you would have other functional groups in a molecule. Therefore, selectivity becomes a very large problem for functionalization. Before we actually move on to the approaches for CH activation, there are certain mechanisms that we should look at. Essentially, there are two major types of mechanisms in CH functionalization. One is the outer sphere CH functionalization, the other is inner sphere CH functionalization. One set of chemists believe that the outer sphere CH functionalization are not truly CH activation. In a way, this is kind of true because you do not have the formation of any organometallic species, or there is absolutely no insertion into the CH bond that is being functionalized. So essentially, you start off with either a metal oxo species, or you start off with either with an imido species or a metal nitrine or a metal carbene species, and there occurs an H atom abstraction followed by a rebound to give you the functionalization. You can also do this, like I said, with metal carbenes and metal nitrines. Mostly this is found with oxo species. With the inner sphere functionalization, this depends on the nature and oxidation state of the metal in the complex. There are a variety of pathways available in inner sphere CH functionalization. In the inner sphere CH functionalization, essentially, you will have a CH bond cleavage occurring and formation of an organometallic species leading to a functionalization. So the overall process actually involves the direct interaction of the metal with the carbon that is being functionalized. Within this, you have electrophilic activation mechanism, in which you have very little of pi back donation and a great amount of sigma donation from the CH bond. Within electrophilic activation mechanisms, you have majorly internal electrophilic substitution and concerted metallation deprotonation. Depending on the ligand and the complex that is involved, you could have either a 4-member transition state or you could have a 6-member transition state. So in the 4-member transition state, essentially, we often define this as internal electrophilic substitution, whereas in the 6-member transition state, we call this as concerted metallation deprotonation. Essentially, both of these lead to the formation of a species of this kind. In another pathway is the 1,2 addition mechanism. This is very often seen with alkylidene or alkylidene complexes, where the CH bond adds across an MX multiple bond, leading to the generation of a new organometallic species. And then we have the oxidative addition mechanism when the electron-rich metals are involved, which involves now a great pi back donation, which dominates over the sigma donation, leading to an agostic type of complex and the insertion of the metal into the CH bond. Because of this, the oxidation state of the metal goes up by 2. And then we have the sigma bond metathesis, in which, as the name suggests, there is a metathesis type of transition state, a 4-member transition state, leading to a new CM bond. Now, between the CH activation, you can have two types. One is the electrophilic CH activation. The other is a nucleophilic type of CH activation, depending on whether the transition metal complex involved is electron deficient or it is electron rich. So based on this, you can actually define whether the charge transfer is, whether the forward charge transfer dominates or the reverse charge transfer dominates. If the metal complex is electron deficient, then the d pi and the d sigma are much lower in energy. Therefore, the forward charge transfer from the CH bond to the metal dominates. Whereas in the nucleophilic CH activation, the metal is electron rich. Therefore, the reverse charge transfer dominates from the metal to the CH sigma star. There is another pathway that is defined by Caro and co-workers, which is called as the eCMD or the electrophilic CMD. The normal CMD favors an acidic CH bond, whereas the ECMD favors a pi basic site. Essentially, this is very similar to an SEAR type of transformation. So when there is an SEAR type of transformation, there is an accumulation of a positive charge in the arene that is being functionalized. So definitely the Hammett rho value, that is the reaction constant, 0. So that indicates that there is an accumulation of a positive charge, or the charge is actually going away from the ring. In both cases, you may observe primary kinetic isotope effect depending on which of the steps is essentially rate limiting. There are a variety of approaches for transition metal catalyzed CH functionalization. You can have an sp3 CH functionalization where you can have directed or non-directed approaches. In the non-directed approaches, the regioselectivity essentially will be controlled by the radical relay and H atom transfer. Whereas in the directed mechanism, the regioselectivity will be controlled by a Lewis basic directing group, as well as the catalyst and ligand combination. In the case of an sp2 functionalization, again, you can have a non-directed or a directed approach. In the non-directed approach, you will have essentially electron-rich arenes, and in some cases, you may have electron-deficient arenes. So this is enabled by a catalyst or ligand design, and essentially one has to be careful about what kind of arenes one is using in this particular case. Here, the regioselectivity is controlled by the steric and electronic properties of the arene. Whereas in the directed case, as I mentioned earlier, you need to use a Lewis basic directing group. This is now enabled by either by proximal groups, or you can have a template or a transient mediator. In both cases, in both the cases, you will need some directing group to bring the metal into the proximity of the CH bond that is going to be functionalized. Whereas in a template backbone, as demonstrated by Maiti and co-workers, you can have a non-covalent interaction with a bifunctional coordinating template to reach into spaces which previously used to be thought as inaccessible for CH activation. And then there are other methods where you can have a substrate-induced chiral ligand catalyst designed to approach spaces which are not usually accessible by normal methods. In the case of directing group approach, one can have a proximal CH activation. One can have a proximal CH activation via a thermodynamically stable 5 or 6 membered metallocycle, or you can have a distal CH activation by using a linker and a very large cyclophane type of transition state, by which you can actually reach spaces which are not in the proximity of the normal space. So you can actually reach meta or para positions of arenes. Not only that, you can actually reach to positions which are not defined as meta or paras. That means you can reach to carbons which are even 6 carbon, you can reach to positions which are even 6 carbons away. There's another approach to do distal functionalization, that is the Catillani approach. You can use a dual CH activation. First, using this Lewis basic directing group, you can functionalize this position. This undergoes a carbopylidation to give you this species. This can now reach this particular H, which is now meta to this position. In fact, this approach has now been used to even functionalize further positions, even beyond the meta position. You can also have another approach, which is called as a traceless directing group, in which you can install a carbonate type of group at this particular position. This can now act as a directing group for the neighboring position, and this can be now decarboxylated at the end of the transformation to give you now a meta-functionalized product. We used some of these approaches very recently in one of the functionalization of ferrocene molecules, where we achieved the 1,3 functionalization of substituted ferrocenes using a template approach, in which we used this particular template and we were able to remove the template at the end of the transformation. In another approach, we used palladium norbornene cooperative catalysis as demonstrated in this particular transition intermediate to achieve once again an enantioselective selective synthesis of ferrocene 1,3 derivatives, and we synthesized some very important, beautiful ligands which were so far inaccessible by normal methods. So in this particular case, this is the enantioselective selective synthesis of a phosphine ligand, which has now a planar chirality, whereas in this particular case, this is a pincer complex, which has now a planar chirality as well as a centrochirality. So this is the first time we've made complexes of this kind by using a distal CH functionalization. In another approach, we can use enolate chemistry for distal functionalization. So enolates can be either in the form of enols, which are transient species, or enamines, or you can have preformed enolates, which are silyl enol ethers, or you can have acetates. Using this particular approach, you can actually pick up a metal at an nucleophilic position or a pi basic site. You can have alpha addition, which is the kinetic product. You can have the gamma or epsilon product, which is the thermodynamic product, because now this conjugation is achieved. That is why this is called as the thermodynamic product. Whereas in this case, the conjugation is essentially destroyed. That is why this is now the most nucleophilic position. However, because this is not very stable because of the loss of conjugation with the ketone, therefore this is now a kinetic product. So this particular approach you can use to pick up an electrophilic metal and carry out a functionalization at the remote position. At the end of the transformation, after reductive elimination, you can get a functionalized group at the distal position with respect to the original group. So this approach we utilized in our group to carry out the gamma arylation as well as the epsilon arylation at variety of dienones and trienones. So you can see here we were able to exclusively functionalize the epsilon position of trienones and the gamma position of dienones. So how does this reaction work? So this reaction essentially works with PD0, starting with PD0 as the active catalyst, and oxidative addition gives you this particular species. Now this enol ether undergoes a very fast silyl-stanyl exchange. This concept we take from Hartwig's work in 2006 to give a stanyl group at this particular position. This now undergoes a transmetallation with this species and a fast reductive elimination, which is governed by the choice of ligands that we take to give the epsilon or the gamma functionalized product. And this concept very recently we have employed in the asymmetric synthesis of C2 spiroindolines, in which we carried out a controlled gamma arylation at this position using an internal nucleophile. We carried out an enantioselective azamical addition to achieve 97:3 enantiomeric ratio in a very useful building block called as the C2 spiroindolines. Okay, so moving forward for today's topic, that is the distal CH functionalization via electrophilic metallation. So what exactly is this electrophilic metallation? If you see Matthew Gaunt's work in 2005, where he started off with indoles and functionalized both the C2 as well as the C3 position of indoles, depending on the solvent that was employed, which indicated that in this particular case, the directing group is not playing a role in the functionalization. So how is exactly this particular reaction working? So this reaction is essentially working because this is now a pi basic site. So this is a pi basic site. It can pick up an electrophilic metal leading to a CH functionalization at this position. We will see some of these mechanisms in a couple of slides from now. Similarly, Yao and co-workers demonstrated the functionalization of pyrroles depending on the reaction conditions and the solvent involved at either the C5 position or at the C2 position of pyrroles. Once again, there is no directing group in this. The N-methyl is not a directing group. It is not a Lewis basic directing group. Essentially, the functionalization is taking place because this is now an electron-rich aromatic, and it can undergo an SEAR type of metallation at either the C2 position or the C5 position. This particular work from Sung-Woo Hong and co-workers in 2013 gives essentially a dehydrogenative Heck or an oxidative Heck reaction at the C3 position of coumarins. If you see the normal reactivity, if this was now a carbopallidation type of transformation, this would not have got at this particular position. So essentially, how is it taking place at this particular position? Why is the C3 position being functionalized? It is happening because, again, you are having an metallation at this position because the oxygen can push its lone pair of electrons at this position, making it pi basic, therefore picking up the PD2 at this position, and then followed by a carbopallidation, beta hydride elimination, regeneration of the palladium to give you the active catalyst. Balraman and co-workers in 2015 also demonstrated an electrophilic metallation in which they were now able to pick up a carbon monoxide at this particular position to generate from anilines quinolines using this particular electrophilic metallation. And then Maji and co-workers also demonstrated the functionalization of this pi basic site. You can see here now this is a pyrimidine. This is not electron rich, but because of this amino group, this pyrimidine becomes pi basic at this site, because of which you can now carry out an arylation at this position, or you can do a dehydrogenative Heck or an oxidative Heck reaction at this position. You can also do a cross dehydrogenative coupling with arenes using 2 amino pyridines. Again, you can see here this amine can push its pair of electrons at this position, making it electron rich. And therefore, you can carry out a metallation at this position, followed by the reductive elimination to give this particular functionalized product. In all of these cases, you can see that there is no directing group involved. It is essentially completely governed by the electronics of the substrate. One of the early works that we carried out in our lab was the cross-dehydrogenative coupling or dehydrogenative Heck reaction of unactivated olefins using dihydropyrans. You can see here both of these are electron-rich partners, and upon coupling, we were able to get exclusively these particular functionalized products without a C2 functionalization. So how is this working at the C3 position? Once again, because we can push the pair of electrons at the C3 position, you can now generate this particular palladium species. This organometallic species can be generated either in a stepwise fashion this way, or you can have a single transition state which gives rise to this particular organometallic species. This can now undergo a carbopallidation and then followed by a beta hydride elimination gives you this particular product, and the regeneration of the palladium catalyst with copper and silver co-oxidant continues the catalytic cycle. So this particular concept, we thought we could take it forward. We were very much interested in arylation at the C3 position of chromines. And then when we carried out this particular work, when this position was singly substituted, to our very big surprise, we found that the arylation actually took place at the C2 position, which was unexpected given the reactivity that one would expect at that particular position. When we carried out this reaction with aryl boronic acids, when R1 and R2 were methyl groups, we found that the arylation expectedly worked at the C3 position. Whereas when we carried out the reaction with aryl iodides or arenes, electron deficient arenes, we found that along with the arylation, we ended up getting a ring contraction. So there needed to be a proper explanation as to how this was actually occurring. So there are a couple of pathways that we proposed, the plausible mechanisms. We're still not very sure what exactly would have happened, but we have a fair idea of how we can explain these particular outcomes. So one of the earliest mechanisms that we thought would be prevalent is that the palladium PD2 could undergo an oxidative addition to give you a very unstable PD4 species, which would now undergo a carbopalladation. Now, because there is no syn beta hydrogen at this position, so therefore this H would be lost. With the arenes, you could undergo a CH activation to give you PD2 species of this kind. This could undergo a carbopalladation, and then a syn beta hydrogen elimination would give rise to the product. And the palladium would now be regenerated with the oxidant. This is one pathway, but there is a problem with this pathway. This PD4 species is not expected to carry out a carbopalladation. So this was a matter of concern. So we thought we have to revise this particular mechanism, and we thought that this is now pushing its pair of electrons, this oxygen, to pick up the palladium at the expected C3 position. After getting this organometallic species, there would be a ring opening at this position, followed by an allynyl palladium species. This now undergoes an endocyclization to generate the palladium at this particular position. This six-membered ring now undergoes an oxidative addition to give you the PD4 species, which undergoes a rapid reductive elimination, or you could have a CH activation with the electron deficient arene to give you this species, which again undergoes a reductive elimination to generate the observed C2 aryl species. There could be another pathway that would be operating. After one has generated this particular species, this could undergo now a 1,2 migratory insertion, followed by the loss of H at this position to give you the same species that we proposed on the previous slide. This can now undergo an oxidative addition or a CH activation with the arene to give you this particular species, which now undergoes a reductive elimination to give you the observed C2 product. When there is a gem dimethyl group and we have employed the palladium catalysis, so essentially once again we propose that the C3 palladation takes place, followed by a 1,2 migratory, followed by the opening of the ring to generate this particular species. This now undergoes a syn oxypalladation. Why syn oxypalladation? Because the product that we have observed is actually a Z product. And if we invoke this particular mechanism, we will definitely get the observed syn product only. Because of this, now this can pick up the aryl iodide in an oxidative addition, or it can undergo a CH activation with this particular arene to generate this species. This can now undergo a fast reductive elimination to give you the observed product. What happens in case of the boronates? The boronates undergo exactly the same pathway when the gem dimethyl group is present. Okay, so moving forward with this particular concept of electrophilic activation, we thought that we could use this particular concept to get an aryl group on the C3 position of an electron deficient heteroaromatic. Quinolines and isoquinolines are pi deficient species. It is very difficult to functionalize the C3 position of quinolines. The most reactive positions of quinolines are essentially the C2 and the C4 positions. You can add nucleophiles to that particular position, both of these positions, or you can carry out a mini-site type of reaction. Normally, it is very difficult to functionalize directly the C3 position of quinolines. So we thought that if we could reduce or we could add a nucleophile to the C2 position, we would generate a species of this kind, which would now become less electron deficient as compared to the parent heteroaromatic. And therefore, now you can make this position as a pi basic position. And once this is a pi basic position, you can actually pick up a metal, an electrophilic metal at this particular position. So this is the concept that we employed, and we used aryl boronic acids as coupling partners to get arylation at this species, at this particular position with the corresponding aromatization occurring in the same pot. So what is the mechanism in this case? The mechanism in this case works exactly as we have seen earlier. This is now the pi basic site. So you pick up the palladium at this particular C3 position. This is probably the transition state for that. Once this species is generated, this can undergo a transmetallation. Reductive elimination generates this aryl species here, which now undergoes a deacetylation in presence of base, and the copper oxidant re-aromatizes it to give you the C3 arylated quinoline. The same particular concept we employed when we were looking into the isoquinolines. So isoquinolines can now be functionalized at the C1 position as well as the C4 position. It's very difficult to functionalize at these positions under normal circumstances. So what we thought is that we can actually reduce one of the bonds or add a nucleophile to this particular bond to generate this dihydroquinoline, isoquinoline species, which using a distal CH activation, we can get arylated species at the C4 position. When we use a proximal CH activation using the N-acetyl as a directing group, we can functionalize at the C3 position. So from a standard substrate, we can actually generate two different outcomes. So with the palladium case, what is the mechanism? The PD2 now undergoes a transmetallation to generate the aryl palladium species, which now is picked up at this particular position, that is the C4 position in an electrophilic palladation, giving rise to this particular species, which now undergoes a reductive elimination to give the arylated compound. This can lose the N-acetyl group under basic conditions. This can reinsert into the palladium, and a syn beta hydride elimination can give you the oxidized heterocycle to regenerate the isoquinoline with the C4 aryl group. In this particular case, we found by NMR that indeed the C4 position was the most electrophilic, was the position where an electrophile would be picked up. And in this particular case, we found that the kinetic isotope effect was actually 0.5. Why is this actually 0.5? Now, what is happening in this particular case? A normal kinetic isotope effect comes from the stretching difference between a CH bond and a CD bond. Okay, a secondary kinetic isotope effect comes from the rate difference from the bending that is in plane or out of plane. Okay, so the secondary kinetic isotope effect comes from the change in hybridization, or it can come from the change in hyperconjugation. Usually, this can be both either normal or inverse. Here, this arises from that particular bond which is not made or broken in the rate limiting step. This is very important. Okay. So if you're changing the hybridization at that particular position from sp3 to sp2, then the out of plane bending, this is the out of plane bending, which weakens as the reaction approaches the transition state, which makes the change in the 0 point energy at the transition state less than the change in 0 point energy in the ground state. So this gives you a normal secondary kinetic isotope effect, which is usually of the value of 1.1 and 1.2. Okay. When you change the hybridization from sp2 to sp3, you are actually strengthening the outer plane bend as the reaction is approaching the transition state, which is making the change in the 0 point energy at the transition state greater than the 0 point energy change at the ground state, because of which you get an inverse kinetic isotope effect, which usually is in the range of 0.8 to 0.9. So you can see here in this particular case, for example, if you are adding HCN across this particular bond, then this is a reversible reaction. What are you getting here? You're starting with sp2, you are going to sp3. So you are from sp2 to sp3, you would expect an inverse secondary kinetic isotope effect, and the observed value for the KIE here is 0.73, which is less than 1. Okay, so what we observed in our case is 0.5. So why do we observe that this is 0.5? In this particular case, if you see the transition state from sp2, we are actually changing to sp3, because of which now we are going into an inverse kinetic isotope effect. And this is precisely what we observe in this particular transformation. So how does the ruthenium catalyzed reaction work? The ruthenium catalyzed reaction, now because we are taking away the chlorine ligand, so this now becomes a cationic active catalyst. Now this cationic active catalyst can bind strongly to a much stronger group as compared to this particular olefin. So this now is comparatively soft, this is comparatively hard. The catalyst here is hard because it's cationic, so it prefers to bind to the acyl group. The acyl group then brings this ruthenium in the proximity of this H, because of which now you get a proximal CH activation. After transmetallation, you get this species. After reductive elimination, you get this particular product, which can now be aromatized to the C3 arylated product. When we carried out Hammett studies, we found that this was a positive value. Therefore, we concluded that the aryl boronic acid, the transmetallation of the aryl boronic acid was most probably the rate limiting step. We also did the order studies in which we found that actually indeed the rate limiting step involved the ruthenium catalyst and the aryl boronic acid, which means that the transmetallation is the rate limiting step. In the case of the palladium catalyst, we propose that the generation of the active catalyst may be the rate limiting step in this particular case. Going back to the quinoline case, you can see here now the quinoline has 2H that can be functionalized. You can carry out a distal functionalization at this position, or you can carry out a proximal functionalization at this position. Why this is proximal? Because this is in the neighborhood of the N-acetyl group. Whereas this is distal, as we had seen earlier, because now this can push its pair of electrons and you can make this a very pi basic site. So when you use palladium catalyst, the palladium acetate in trimeric state is pretty covalent, and it is soft as compared to the ruthenium catalyst, which is cationic. Therefore, the cationic catalyst is hard. A hard-hard interaction leads to a proximal functionalization, whereas a soft-soft interaction leads to a distal functionalization, as we can see here. So we were able to successfully do the functionalization at the C3 position with palladium catalysis. So how does this work in this particular case? This ruthenium catalyst prefers the hard center, which is this center, giving you the olefination at this position via a migratory insertion, that is carbopallidation, followed by beta hydride elimination. And then subsequent steps regenerate the active catalyst. Whereas a soft-soft interaction gives you this C3 palladium species, followed by a carbopallidation, beta hydrogen elimination, and regeneration of the catalyst. In this particular case, we found that the kinetic isotope effect was approximately just about 1, indicating that one of these particular steps may be rate limiting. One of the works that kind of gave us a proof of concept for our approach is this particular work, in which we carried out a catalyst control in a positional selective CH alkynylation of isoxazones. So what did we do here? With palladium catalysis, we functionalized this particular position, and the product we oxidatively took forward to generate pyrroles. We'll see the mechanism in 2 minutes. Whereas with a rhodium catalyst, under cationic conditions, we were able to functionalize the proximal position. So now this becomes the proximal position for this hard directing group, whereas this is the distal position for this particular oxygen, because there is no way you can direct it to this particular position. The only way you can direct it by pushing this particular electron density to this carbon, that is the C3 carbon. Okay, so how does this work? With the rhodium catalysis, like I said, this is now going to be a hard interaction. So you generate this particular rhoda cycle, carbopallidation followed by reductive elimination. Carbopallidation followed by beta hydride elimination gives you this olefin, or you can also have a proto-demetallation to give you the hydroarylation product, depending on the reaction conditions and the substrates. And the regeneration of the catalyst using copper as the oxidant gives you the active catalyst. Whereas in the palladium case, now you have an electrophilic metallation. In this particular case, the kinetic isotope effect was just about 1. We get this palladated species, carbopalladation, followed by beta hydrogen elimination, which was found to be RDS. We'll let you know why. And then you get the olefinated product at this particular position. This now coordinates with ruthenium, undergoes a ring opening to generate an imido species, which undergoes a 1,5 cyclization to generate the pyrrole upon rearomatization. So Lu and co-workers in 2022 actually provided the proof for this particular transformation. That this particular transition state is actually valid where there is a hard interaction of the cationic rhodium with the nitrogen, thereby functionalizing the proximal position. Whereas in the case of palladium, they found that this hetero-dimetallic species was formed, which functionalizes the distal position of the iso-oxazole. In both the cases, the other transition state was found to be much higher in energy. For example, for the proximal functionalization versus the distal functionalization in case of rhodium, this was found to be much higher in energy. Whereas in the case of palladium, this particular was found transition state was found to be much lower in energy as compared to the proximal functionalization. Not only that, in this particular case, in the rhodium case, for the distal functionalization, this transition state was found to be quite distorted. Very quickly, I will go through one final project that we very recently did, is the functionalization of quinolones using cyclopropanols. So in this particular case, we were expecting an electrophilic metallation at this particular position, and a hard interaction would lead to a functionalization at this particular position. So when we used rhodium catalysis, we got exclusively the functionalization at the C3 position. When we used ruthenium catalysis, surprisingly, depending on the electronics of the cyclopropanol, we achieved either the C3 functionalization or the C4 functionalization. In case of electron-rich cyclopropanols, we observed C4 functionalization under ruthenium catalysis, whereas when these are electron deficient, we obtained the C3 as the major product. Whereas, like I said, with rhodium catalysis, we got exclusively the C3 functionalization. And the proof actually came from DFT studies and a couple of control reactions that we did. I will not go through all of those. Very quickly, I will just run you through the mechanisms that are involved in this particular transformation. In the proximal functionalization, there could be 3 pathways. So you could have the active catalyst that is being generated, a CH activation at the proximal position. This species, the homoenolate, is generated from the ring opening of the cyclopropanol, which now undergoes an oxidative transmetallation to give you a bimetallic species of this kind. Reductive elimination, which we found by DFT studies to be rate limiting, would give you the product and the regeneration of the catalyst. In another pathway, this particular complex, this copper complex, would lead to the generation of an enone from this cyclopropanol. This would now undergo a coordination with this Rudena cycle. A migratory insertion followed by proto-demetallation would give you the C3 alkylated product and the regeneration of the catalyst. Or from the cyclopropanol, this Rudena cycle could coordinate, undergo a beta carbon elimination to give and a reductive elimination to give you the C3 product from this species, or this species 3 could undergo a beta hydrogen elimination to give you this coordinated enone. This could undergo a migratory insertion to give you the C3, one more Rudena cycle. This Rudena cycle would now undergo a proto-demetallation to regenerate your ruthenium catalyst, followed by the formation of the product. What about the C4 product? How does the C4 product generate? We found that this now generates this particular copper species, followed by a bimetallic species that is coordinated to this olefin. A 1,3 alkyl migration generates this Rudena cycle, which now undergoes an anti-E2 type of elimination to give you this species. This is now broken down by methanol to give you the C4 alkylated species. So this was found in collaboration with our collaborators, Dean Tantalo from UC Davis and co-workers. And this actually tells us that it's not always that one expects a CH activation to be the major pathway in the reaction. To our great surprise, we actually found that this particular work led us to conclude that probably a triplet state was involved in the C4 functionalization. So I'd like to end by thanking all my co-workers, past and present. And I'd like to thank the funding agencies, especially SERB, CSIR, and my host institution, ISER Bhopal, for the generous funding. I'd like to thank our collaborators, Luigi Cavallo from KAUST, Dean Tantalo from UC Davis, and Manoj Bane from Jain University. And I'd like to thank all of you for your kind attention. Thank you.